Third motivation, if you will, for using polymer EVAR, it's a simple one, but I think there's just a couple key points to make here. One of them is, on the left here, you can see a schematic of a conventional EVAR device. Springs and fabric. And if I take the catheter that delivers this device and I look anywhere inside here, basically cut the catheter and look inside, I will see stent struts in the cross-section and I'll see graft material in the cross-section. And pretty much all throughout the length of this device, that's what I see. And these are all about 20 French. It doesn't matter, Medtronic, Cook, Gore, etc. They all are wire fabric devices. Springs pushing fabric to seal and create friction. They're all give or take about a French or two. It's not surprising they're all around the same profile. They are the same technology. There's the same fundamental mechanism of action, and nobody has a magic material that only they have. They're built with the same materials, with the same architecture, so they're all around the same profile. Here's ovation, and if you imagine what that looks like inside a catheter. If I were to cut the catheter in here, where this anchor stent is all I'd see would be metal struts. And if I cut the catheter somewhere in here, where the aortic body section is all I'd see would be PTFE fabric. I don't even see polymer. It's not even there yet. So the secret sauce, the stuff we're even talking about here, is not even present in the catheter yet. So that's how we can construct a device like this and put it into such a small catheter. So this prosthesis is delivered in this catheter because we're separating and optimizing, and not only functionally, but spatially and temporally. So we aren't even putting in the polymer yet. We've achieved low profile not by just we're not putting less material in, we're just not putting it in all in the same place at the same time. Huge fundamental difference. So we can construct a prosthesis in the aneurysm with as much material as we want without needing a bigger diameter delivery system to get it there. What does that look like compared to these other devices? This is a scale drawing showing the outside diameter of the delivery systems of all these devices. Here's ovation, and here's the other ones. So most of the time, ovation's going through vessels that are fairly bigger than the catheter, whereas these other devices, much of the time, they're going in vessels that are smaller than the catheter, creating more opportunity for complication. These percentages, all the way down to ovation for 83, that represents what fraction of patients with AAA have access vessels at least as big as these catheters. And you can see with some of these bigger technologies, maybe only a quarter or a third, or maybe best case, half the patients even have access vessels big enough to receive these catheters without being dilated, stretched, or otherwise deformed. Whereas with ovation, 83% of the time, you've got access vessels bigger than the catheter. And perioperative access vessel complications are still the most common complication in EVAR. And so if you can have a much less invasive therapy, it would make a difference.
The design principles used to build the AFX endovascular AAA system are fundamentally different from all other EVAR systems. The AFX system's innovative design uses the unique approach of separating the seal zone from the fixation zone, making it well-suited to treat a wide range of challenging anatomies. Anatomical fixation enables the preservation of the native aortic bifurcation for future clinical access. Placing the flow divider directly on the native bifurcation negates migration forces and eliminates the need for mechanical proximal fixation and excessive radial force. Active Seal technology uses a highly conformable, multi-layer DuraPly EPTFE material designed for strength in every direction. The AFX system is the only commercially available endograft with the fabric on the outside of the stent. Secured at the proximal and distal ends of the stent graft, the material is able to move independently of the stent. Driven by the pressure gradient between the aorta and excluded aneurysm sac, the material opposes and actively conforms to the aortic wall, extending the effective seal zone beyond the anatomic neck. Challenging anatomies demand versatility. Therefore, the AFX system is versatile across anatomies. The AFX system's large on-IFU oversizing range and its DuraPly EPTFE Active Seal technology make it ideally suited for reverse tapered neck anatomies. In anatomies with aortic neck thrombus, the AFX system's anatomical fixation and Active Seal features produce low radial force and high conformability to the irregular neck. In anatomies with narrow distal aortas, the anatomical fixation design eliminates endograft limb competition created by competitors' proximally fixated graft systems and has shown a low risk of occlusions. The AFX endovascular AAA system, consisting of the AFX2 bifurcated delivery system and Vela proximal endograft system, provides simplified delivery, streamlined deployment, and confident control. The AFX endovascular AAA system offers a fundamentally different design to precisely address the needs of challenging anatomies.